This week we're going to cover torsion, and we're going to start off with a very simple example. First of all, though, let's cover some definitions. So we should recall what torque is. It's basically a moment, so force times the distance, that tends to twist a member along its longitudinal axis. So torsion just means that when you have an external torque and it's applied to a shaft, it's going to end up creating an internal torque within the shaft, and that's typically what we're going to be solving for. So kind of to visualize what torque is, you have a shaft and you apply torque on the ends like you're twisting a rod, and it kind of deforms longitudinally. So you can kind of see an example here as well. If you twist a straight rod, you can see the deformation afterwards. Yep. So some equations. The most important is tau, or shear stress, equals Tc divided by J. So tau is the shear stress in the shaft. T is the resultant internal torque. So that's typically what we're going to be solving for. J is the polar moment of inertia, and then C is always the outer radius of the shaft. So for polar moment of inertia, we have two equations, pi over 2 c to the fourth, where C is the outermost radius. So this is used for a solid shaft, so C would just be your outermost radius, and then pi over 2 c outer minus c inner. So this is used whenever you have a hollow rod. So you would use the inner radius and the outer radius to calculate the polar moment of inertia. So this is for a solid shaft, this is for a hollow shaft. Okay, so another important thing to remember is sign convention. You always have to use the right hand rule to determine the direction of your internal torque. So if you have a rod like this and your positive x-axis is this way, your positive x-axis is always going to be where you cut the beam and point outward from where you cut the beam. So if I have a long beam and I cut it here, so this is my cut, I'm going to point my thumb outward, and the direction in which I rotate or point my fingers, that is going to be the positive direction. So when I point my thumb outward, I curl this way, so this is positive torque. In this case, if I cut the beam here and decide to look at the right section, I point my thumb outward and my fingers curl this way, so the positive torque is going to be clockwise. So it's very important to remember that you cut the beam, point your thumb outward from the cut, and wherever your fingers curl, that is the positive sign convention. And you'll see what I'm talking about when we do this problem. So we have a shaft shown, and it's supported by two bearings. It's subjected to three torques. Determine the shear stress developed at points A and B located at section AA of the shaft. So we have this shaft, we have these three different torques, and they want us to find the shear stress in this section right here. So basically we have to cut the shaft exactly at this section, and they give you a zoomed in view of this section. When you cut it, point A is located on the outermost radius, and point B is located 15 millimeters, so that's a 15 millimeter radius. Okay, so here's our problem. What do we know? So we know our equations. So shear stress is what we're looking for. So shear stress equals Tc over J, and J equals pi over 2c to the fourth. We also know that for point A, the radius is 75. For point B, it's 15. So what do we want to find? We want to find, in order to find the shear stress, we need to find the polar moment of inertia and the internal torque. So I'm going to start with the polar moment of inertia because it's pretty straightforward. We have a solid shaft here, so pi over 2c to the fourth, where c is always the outermost diameter, or the outermost radius. So in this case, point A happens to be the outermost radius, so we use 0.075 meters. Always convert to meters from millimeters to meters when doing your equations. So I end up with a polar moment of inertia of 4.97 times 10 to the negative fifth meters to the fourth. Okay, so I've solved for J. The only thing left to solve for is T. So to solve for T, I basically take the rod, I cut it, and I choose to look either at everything to the left or to the right. In this case, I chose the left, but you can also choose the right. It'll be the same analysis, you'll get the same answer. So I cut it, look everything to the left. So I have 4250 kilonewtons per meter. I have another one going the opposite direction, 3000 kilonewtons per meter. And then what I do is I can logically analyze. You know, I have 4250 going this way and 3000 this way, so I must need some other torque pointing in this direction to balance out the 4250. So I write my sum of the moment equation. So if I point my thumb outward, my fingers end up curling in the counterclockwise direction. So counterclockwise is going to be the positive sign convention. So this is counterclockwise, so it's positive 4250. This is counterclockwise, so it's minus 3000. And T here drawn in is also counterclockwise, so it's minus T. So once I solve, I end up with T equals 1250 kilonewtons times meters. And because it is positive, it means that the way that I drew it is the correct convention. So my T is 1250 kilonewtons per meter clockwise. Okay, another way that you could have analyzed this is cut it, right? But instead of drawing your T this way, you could have drawn it the other way. And remember, here, still, if you point your thumb in the X direction, in the positive X direction, your fingers will curl counterclockwise. So anything counterclockwise is positive. So positive 4250 minus 3000 plus T, because T here now, the way we drew it, is counterclockwise, so it's positive. So when I solve, I end up with T equals negative 1250 kilonewtons per meter. What does that mean? Because I end up with a negative, it means that the way that I drew my torque is actually not right. It should be the exact opposite way. So in reality, I end up with basically the same answer. My torque should be 1250 kilonewtons per meter clockwise. So no matter which way you draw in your torque, you will end up with the correct direction as long as you follow the sign convention of the right-hand rule. Now another thing you could have done is you could have cut the beam and looked at everything to the right, which would have been even more simple because here you only have one torque. You have 1250 kilonewtons per meter. And it'd be helpful if you guys want to do it that way and make sure that you're getting the right signs. You'll get the correct magnitude no matter what, because 1250 is the only other torque there, but make sure that you understand the sign convention. Okay, so we found our T. So the next thing is, what do we know? We know the T, we found J, we know our C, so now we can basically plug into the equation. So to find the shear stress at point A, I plug in T, which is 1250, times the radius at point A, which was 75 millimeters, divided by J, which is the polar moment of inertia. So I end up with 1.89 gigapascals. That is the shear stress at point A. Do the exact same thing for point B. I plug in the 1250. We don't need to worry about signs here because they're just asking you for a shear stress, a magnitude, right? It's going to be positive. Don't worry about the signs, but the signs will play a role later on as we move on to angle of twist. So plug in T. The radius at B was 15 millimeters, and the polar moment of inertia is the same. The polar moment of inertia is always going to be pi over 2 times the outermost radius to the fourth power. So no matter what, it's going to be the same for every point. So I end up with 0.377 gigapascals, and remember, giga is times 10 to the 9th. Okay, so pretty straightforward, I hope. the main things that you will need to find is your internal torque and J. And I would say internal torque is the hardest part.